Let's talk about the two important trig identities for year one. Here they are. Sin squared x plus cos squared x equals 1, and tan x equals sin x over cos x. Just a quick note on these symbols here. The three lines mean identical to. So that means these statements are true for all values of x. And that's why we call these things identities rather than equations. That's just background information. Let's get into some examples. Example 1, show that 1 over cos theta plus tan theta is identical to cos theta over 1 minus sin theta. Now this is a proof or a show that, so it's best to start with one side of the equation and then end up at the other side. I'm going to start with the left-hand side, LHS. On this side, I'll keep the 1 over cos theta. I'll change the tan theta into sin theta over cos theta using this identity. So now we have this. The denominators are the same, so we can add those together to get 1 plus sin theta over cos theta. And then from here, I'm keeping an eye on the right-hand side, and I can see that I want a cos theta in the numerator. So to do that, I'm just going to times the top and the bottom of this fraction by cos theta. That way I'll get that cos theta in the numerator. With trig proof, it's okay to not have it all planned out. It's best just to write something down and see where it takes you. So now we've got cos theta, 1 plus sin theta, all over cos squared theta. This is good news because now we can replace the cos squared theta with 1 minus sin squared theta using that identity rearranged. At this point, we have cos theta 1 plus sin theta in the numerator, and then 1 minus sin squared theta in the denominator. Again, from the green identity rearranged. At this point in the denominator, I'm actually seeing now that special case, dots, difference of two squares. It's great news because it means we can factorize it into two brackets, 1 plus sin theta, 1 minus sin theta. Put the top on again. Notice these two brackets match, so we can cancel them. We're left with just cos theta over 1 minus sin theta, which is the right-hand side, RHS, and we're done. Example 2 is about solving a trig equation. I've made another video on solving simpler trig equations, so I'd recommend you watch that one first if you haven't already. This example says find all values for x in the interval between 0 and 360, for which 3 tan x equals 4 sin x. Give your answers to one decimal place where appropriate. So first thing I'm noticing is that we have a tan x and a sin x in the equation. This is bad. Can't really solve an equation easily if we've got more than one trig function in there. So let's try to replace the tan x with sin x over cos x using that second identity. Now we can multiply up the cos x to get 3 sin x equals 4 sin x cos x. Then we can move everything over to the left. And then we can factorize out the sin x. Now here we have quite a common situation. So we've got something times something else equals 0. This does happen quite a lot in maths, and the only way that's ever going to be true is if one of those things themselves equals 0. Because if you think about it, 0 times anything is 0. Therefore, that leads us on to two separate equations to solve. One of them is sin x equals 0. So let's get those solutions first. Inverse sine of 0, x equals 0 to begin with. And then you can draw a sketch to find the rest. There's sine 0, 180, 360. So sine x equals 0 here, here, and here. However, just watch out. We actually don't want to include 360 in our answers because the original range up there did not include 360. Therefore, here we've got 0 and 180 as valid answers. The other equation to solve was 3 minus 4 cos x equals 0. When you rearrange that, you get 4 cos x equals 3. So cos x is 3 over 4. Therefore, x is inverse cos 3 over 4. When you put this in the calculator, you get 41.41 for the first answer. And we use a sketch to find the rest. Here's cos is 3/4 roughly. Got two solutions, 1, 2. That first one must be the 41.41. And then to find the second one, we just do 360 minus 41.41 using the symmetry of the cos graph there, which is 318.59. Now it's just a case of putting all the answers together. I like to put my answers in numerical order. So to one decimal place, the final answers are 0, 41.4, 180, 318.6. And that's it. Last example, find all values for x in this interval for which 2 cos squared x minus 3 sin squared x equals 14 cos x. Give your answers to one decimal place. So for this one, we've got a mix of cos squared x, sin squared x, and cos x. So it probably makes the most sense to replace the sin squared x and try and get it in terms of cos. To do that, we can use that first identity rearranged. And that will give us 2 cos squared x minus 3 brackets 1 minus cos squared x equals 14 cos x. And again, that's just from the first identity rearranged. Then we got 2 cos squared x minus 3 plus 3 cos squared x equals 14 cos x. Bring it all over to the left and simplify. And here we have a hidden quadratic. You can solve these straight away if you want to, but I like to make a substitution. So I'd say something like y equals cos x, and therefore it's 5y squared minus 14y minus 3 equals 0. From here, you just solve it using your preferred method. And when you do that, you get two answers. Y is 3 or y is minus a fifth, which means then that cos x is 3 or cos x is minus a fifth. This first one, cos x is 3, is invalid. And that's because, as we know, the cos graph only goes between 1 and minus 1. So that one you can ignore and instead focus on cos x equals minus a fifth. So x would be inverse cos minus a fifth. Put that in the calculator, you get 101.54 for the first answer. Use a graph of cos minus a fifth down here somewhere. Two answers, here and here. The first one must be our 101.54, and the second one we get from doing 360 minus 101.54, which is 258.46. So two final answers to one decimal place, 101.5 and 258.5, and that's it. That's it for now. If you found this video useful, please do remember to like, comment and subscribe to my channel if you haven't already. And do share this with anyone else you think might find it helpful. Thanks, and see you next time.